Hi everyone, this is Billy. A while ago I created this prototype of a Variometer FM Crystal Radio. It did work, but reception is not that great. It's very hard to hear the FM broadcast. So I think about other alternatives. Then using Fusion 360, I designed this 3D design to print out the frame for the Crystal Radio. Before we continue, please support my work by clicking like, subscribe, share with your friends, and click the bell so I can notify you for any future projects. So this is the 3D printed design that I used for the FM Crystal Radio. There are two coils in the middle. The middle one will rotate inside the big one. When it rotates, it reverses the direction of winding, so the mutual inductance created will be a complete reverse. By varying this position of the inner coil, we can vary the inductance from a minimum to a maximum range. If you pair that up with a fixed capacitor of say 10 pF, the whole resonance circuit can be tuned by just rotating the inner coil. Here is the circuit. The top one is for use with MOSFETs 3DQ, the bottom one to be used with any diode that can work in the FM frequency. The thing that determines whether you can use it is the junction capacitance of that diode. It has to be very low. Otherwise, that capacitance will be added to your tuning circuit and knock it outside of the FM frequency range. First, let's look at the diagram on the top for the MOSFETs. Starting from the left, you'll see two antenna terminals, A1 and A2. If you're using a telescopic antenna like 1.2 meter long, you can try either one of the terminal. Or you can connect one terminal to the telescopic antenna, another terminal you can connect to a around 1 meter drop-down cable to form a dipole. If you're using a Yagi antenna, the big one at home, like around 1.7 meter long, you can connect the two terminals from your Yagi antenna to A1 and A2, so you get the maximum volume. Moving further to the right, you get two coils. They are L1 and L2. There's a slanted arrow there. That means it's a variometer type of coil, where the inductance will change. L1 is the smaller coil that rotates inside the bigger coil, L2. I will show you in the video how to make it, but you can refer to the small text at the bottom of the diagram where it says L1 is actually a 1.5 turn coil with a diameter of 20 millimeter. L2 is a 2-turn coil, diameter of 25 millimeter. Both are wound using 0.8 millimeter magnet wire. C1 is the fixed capacitor that will pair up with the coils to form a resonance circuit that will be in the FM frequency range. Depending on what frequency range you use for FM broadcast in your country, it can be 8 pF or 10 pF. Let's try it out to see which one works. I am using ceramic fixed capacitor, but you can get a much better quality if you try to use those ATC, high Q factor, SMD, surface mounted device type of fixed capacitor. I have a few of those that I use for my Q meter, but I just haven't got the right range to use at this time. I order it. When it comes, I'll try to replace it and see how best it can improve the quality. Moving further to the right, you got the detectors, right? On the diagram on the top is the 3DQ MOSFET, also called 3SK143-Q. The MOSFET has 4 terminals, 2 gauge terminals called G1 and G2, and the other 2 terminals called S for source and D for drain. Basically, you can assume that S and D are just like the 2 terminals of a diode. So starting from G2 is connected to the hot end of the coil L1, the top of L1. G2 is connected to the common ground of the circuit, which is the first turn of the coil L2. And then you have the S terminal, the source terminal, which needs to connect to some tapping point of the coil. You can try it out, but as far as we try, it works best if you connect it to the second turn of L2. So just one turn above the common ground, one turn above the tapping used for G1. Okay, and then you have the output, the drain. So D stands for drain, which will give the output of this circuit. The output will connect to the audio jack. Then there's a fixed capacitor around 200 pF to suit the FM frequency range to smooth out the audio output by removing the high frequency radio frequency component of the audio output. So because 200 pF will offer a bypass path for the alternate circuit or the radio frequency signals to go through that at a low impedance, lowest resistance, rather than going through J1 and going to a headphone that has a higher capacitance. The radio frequency will just choose the path of the 200 pF, going back to the common ground. So by doing that, we kind of filter out the radio frequency, leaving behind the audible signals in the audible frequency. In terms of the headphones or earbuds you can use a piezoelectric earbud, which you can make out of a piezoelectric buzzer. I have a few videos to teach you how to make one. It is very easy and the quality is quite good. Otherwise, you can find some moving iron magnetic headphone or earbud that have a big coil. So the impedance of those usually is not too high. It can be as low as 20 or 30 or as high as 1K or 2K . But the higher the impedance doesn't mean the sensitivity is also higher. So it's a common myth. Sensitivity and impedance or resistance has no relationship. It depends on the quality and the methodology you use to make your earbud or headphone. Some of the very sensitive headphones or earbuds are of a low impedance, like 50 ohms. But however, some of the very high impedance headphones, like the piezoelectric earbud, they are of impedance of around 10K or 20K. They may not be as sensitive. However, I have been very lucky. I bought a very sensitive piezoelectric microphone from Osaka, and I've changed it to become an earbud, but adding a earbud tip. I will share the video how you can make it yourself. But first, you need to find that very sensitive piezoelectric microphone. I don't know where they sell it, but I've bought it from a electronic component shop in Osaka. It's quite cheap the way I bought it, 500 yen. I don't know whether I can find it anymore. But let's go back to the circuit. So we finished talking about the MOSFET circuit. Let's go to the bottom one, the diode circuit. You can see the left part of the picture is the same with the resonance coil, the variometer L1 and L2, and then the fixed capacitor, they are the same. The only difference is you connect a diode to either the point B or the point C, depending on the situation where you are getting better reception. In general, point B will give you higher sensitivity. That means you are able to tune into some station easier. But that has a drawback that selectivity is very low. That means you will hear multiple stations mixed together. If you choose to connect to point C, selectivity will increase, but sensitivity will drop. That means some of the weaker stations you may not be able to hear it anymore. So that's why you can choose to connect it to either point. Because I'm using a 4-pin socket that will fit both the diode or the MOSFET, you can insert the diode in the right pin number in that socket to connect to either point B or point C. Just look at the MOSFET circuit diagram and choose which pin of the MOSFET you want the diode to connect to in that socket. I forgot to say something about the output. So in case you can't find the matching impedance, earphone, earbud or headphone, you may need to use some step-down transformer. If you're using a diode, the diode's output impedance will depend on each diode. Some are around 5K, some are up to 100K, right? It depends on which diode you are using and which tapping point on the FM resonance circuit, resonance coil you are tapping into. So you have to try it out. We do have some selectable transformer circuit that you can buy a transformer with multiple tapping points, so you can select the right impedance. I will put a link there for such a device that you can make yourself, so you can try to match the best impedance, so you can harvest most of the energy from your radio that will fit into the earbud or headphone. Then you can hear very good output signal. To make this crystal radio, first go to my Fingerless homepage and download these 3D print files. First file you need to download is the chassis, called FM chassis. Just print it like the way I show here. It needs 3 hours to print. The second file to print is this for the knob, called FM knob. So this one prints in 13 minutes. While we are printing, you can prepare a few things. First, find some M4 screws that are made of copper. Then put some solder on the edge, so we will be able to connect a wire there later. If you can't find the copper M4 screw, you can use the stainless steel one, but it will be very hard to solder it. In that case, you may need to find some other ways to connect the antenna terminal there, like using a filler. You can screw the M4 screw into the holes in this FM crystal radio frame after you get it printed. These are for the 2 antenna terminals, A1 and A2. Let's test it out to mount this telescopic antenna, which also have a M4 hole there. Okay, just make sure it fits nicely and is stable. Next, we need to solder the detector with the audio jack and also the fixed capacitor. There are 2 of them. One is 200 PF, the big one. The small one is 10 PF. So after soldering, we need to fit it into this frame like this. Then we can stick it together using the regular glue. Then we need to create the 2 coils, the bigger one and the small one. We need to find 2 frames to be used to wind the coil. The left one, for the smaller one, I'm using the 18 millimeter diameter one. For the big one, I'm using this, which is 23 millimeter diameter. I'm using this magnet wire, 0.8 millimeter, to wind the 2 coils. Then for the interconnecting piece that connects the big coil with the small coil, we need a small spring, so when it rotates, it won't break the wire. For that spring, we are using this thinner wire, 0.3 millimeter. Let's go ahead to wind the big coil first. So we need to wind 2 turns like this. Then cut the loose wires. Let's fit it into the slot for this big coil. See if the size matches. Next, let's wind the smaller coil. This is 1.5 turns. Then let's fit it into the frame to see if there's anything blocking the movement. Next, let's use the solder iron to put some solder on both ends of the coil and the 2 contact points in the middle. So we need to turn the heat to around 350 degrees Celsius so it can be hot enough to melt the paint on the outside. Alternatively, you can use sandpaper to sand it out, but it will not be as nice. So I recommend you just use the solder iron to do it. The 2 soldering points is used to connect to the 2 connections from the circuit. Now we are using the 0.3 millimeter wire to wind a spring around 2 turns that will interconnect the big coil with the small coil. Then we need to solder them together. This is the part that is the toughest because you need to finish soldering and allow the small coil to turn freely within the big coil to avoid too much resistance. Next, we need to do the same on the other end of the small coil, but this time the spring is not connecting back to the big coil. It's left there like that. We will connect to the rest of the circuit. Now let's mount the big coil and the small coil into the frame. So we make use of the small holes to pass through the wires. And then for the small coil, we need to fit it in with that knob. There's a tiny hole in the knob. You can push it into the 0.8 millimeter wire and make it very secure. Now let's mount the small coil there. You may need to push and bend the wire a bit before you can put it in. Make sure after you pull, you make it straight again. And most importantly, insert the knob. And the knob should be able to rotate the smaller coil without any resistance and not getting loose as well. Now let's make all the circuit connections. There are 5 holes connecting the frame to the rest of the circuit, and each hole is to pass 1 wire. So after connecting and soldering, here's how it looks. Before we start the testing, let's take some baseline by testing the existing crystal radio, the FM crystal radio that I have first. Now let's test our 3D Variometer FM Crystal Radio. This is the 3DQ MOSFET. Let me insert it back. To avoid people saying that this is fake, I duped the audio, so I just unplug all this connection to make sure you know it's real. The recording is done using my impedance matching transformer for the iPhone recorder. There's no active component involved. Now let me test with the diode. In this configuration, I am testing with the diode connecting to point B of the circuit. That means directly onto the hot end of the coil. Now let me connect the diode to point C, which is at the tapping point of the coil. Let me switch to another type of diode that I got. Let me switch back to the 3DQ. So this is approaching the end of my testing. You can see this design really produced a usable FM crystal radio. The actual usage, sometimes I will hear very clear broadcast, sometimes it's a little bit blur, depending on the weather and other situation. Because of the recording, some of the audio output is lower or distorted. But when I actually use it just without the iPhone connector, just using my crystal radio earbud, the quality is quite okay. I hope you like this project. If you like my videos, please support me by clicking like, subscribe, share with your friends. Don't forget to click the bell so I will be able to notify you when I have a new project. Thanks a lot for watching. This is Billy. You are watching the Billy C DIY channel.